Hello everyone, I am Xiao Zhang from North Carolina State University, and today my topic is design of high-frequency broadband CMUT arrays. And this work was supported by DARPA and NIH. This morning there was a question about the bandwidth, especially at high frequency for CMUT arrays, and I hope this math speak can provide some more useful information to the question. For the applications where deep penetration is not required, such as intravascular ultrasound imaging, ophthalmology imaging, and small animal imaging, high-frequency broadband ultrasound arrays are required for the high resolution in both axial and lateral directions. In this presentation, the background and the motivation will be first introduced, and then we'll present a high-frequency broadband 1D CMUT array. In the second half of the presentation, we are going to discuss the design guidelines for high-frequency broadband CMUT. The traditional method to make ultrasound transducers are based on piezoelectric technology, and as the frequency increases, the array pitch needs to be tens of microns. And the traditional dicing method will be difficult to achieve such a small size. That's why the laser cutting and deep RE technologies has to be used. And also the crystal thickness needs to be tens of microns. Those forms the challenges on the fabrication side. And additionally, the increased coupling could be observed depending on how the curves are filled. And finally, it is difficult to achieve wideband operation for piezoelectric transducers. CMUT technology offers advantages for making high-frequency broadband transducers, mainly because, first of all, the small device dimensions can be well controlled by the photolithography technology, and the densely packed elements can be defined by the lithographic patterning. And also, it is well known that the wideband operation is easier to achieve for CMUTs. And the crosstalk between the neighbor elements can be minimized. High-frequency CMUTs has been reported before, but it has also been shown that for high-frequency CMUTs, the broad bandwidth is more difficult to achieve. So we have recently reported a process which is a 3-mask process to fabricate vacuum-sealed CMUTs using anodic bonding. This process has a really simple process flow and can reduce the parasitics by using a glass substrate and metal bottom electrodes, which is very critical for high-frequency applications. And in this presentation, we are going to use the same process to fabricate a 1D high-frequency broadband CMUT array. And the key feature of our 1D broadband CMUT array is the reduced gap height. The reason for the small gap height, we'll explain that in the second half of the presentation. This is the simplified process flow. We do the first photolithography to pattern the bottom electrode and also the active area. And we etch the glass by BOE solution and deposit metal in the cavity to target for 15 nanometers gap height. And we perform anodic bonding after that, and remove the handle and box layer. After anodic bonding, we observe the trapped gas inside of the cavity, which is due to the oxygen generated during the bonding. In order to evacuate the gas and also reach the bottom electrode, we perform the second photolithography to etch the pads. The gas is evacuated at the same time, and the whole wafer is resealed by PECVD silicon nitride. The third photolithography is done in order to etch the silicon nitride on the top and bottom electrode for electrode's axis. And finally, we deposit 20 nanometers chromium and 180 nanometers gold to form the electrode contact. We have shown that we can define a thin gap across the wafer. The AFAM image shows that the 15 nanometers gap before anodic bonding, and the SEM image shows we can achieve a 15 nanometers gap for the final device. This page shows the fabricated 1D CMUT array. The physical parameters of the array is summarized on the table, And the picture shows the fabricated 1D array and also the array elements. We characterize our device in immersion. The element was biased at 50-volt DC and excited by a spec-type pulsar. A hydrophone was used at a distance of 1.8 millimeter to receive the signal. The figure on the left shows the received signal, and the peak-to-peak pressure on the CMUT surface is calculated to be 600 kilopascal. The frequency spectrum is shown on the right figure, and from here we can see that we can achieve a 29 megahertz center frequency with 100% fractional bandwidth. And we propose we can keep this broadband operation at a higher operation frequency using our current process. And in the second half of the presentation, we are going to show the design guidelines for high-frequency broadband CMUT design. The first thing to realize is that we have different, we actually have a flexibility to choose the thickness and the width combinations to obtain the same operation frequency in air. As an example, for a mechanical resonant frequency at 60 megahertz, we have the different combinations for the silicon plate thickness and the radius. For the figure on the right shows the immersion operation. And we can see that with a thinner plate and a smaller cell size, we can achieve a wider bandwidth, although the sensitivity will be compromised. Please note that the fill factor for the three designs, they are equal and equals to 60%. This is because this is another important aspect for broadband operation. And this leads us to the next discussion. It has been shown that a low fill factor will deviate the CMUT behavior away from the desired piston-like behavior. Therefore, in order to achieve a higher fill factor and higher and a broader band, the process should allow us to reduce the cell-to-cell distance. For the conventional sacrificial release process, the fill factor is limited mainly because of the etching holes. The fusion bonding method can actually increase the fill factor. It typically requires around 5 micron wide post. But for the high-frequency CMUTs, this becomes comparable to the cell size. And for anodic bonding, we have successfully bonded to a 2 micron wide post in a test run. The AFM image shows the 2 micron wide post before bonding, and the optical image shows the plate bonded on the 2 micron wide post. As the cell size and as the plate size decrease, we should also scale the gap height as well in order to achieve a low operating voltage. We desire to achieve a voltage less than 50 volts in order to integrate the CMUTs with electronics. And additionally, the efficiency of the CMUTs won't be compromised at high frequency only because of the thin gap. And the 2 megapascal output pressure can be generated with only 5 nanometers average plate displacement for 40 megahertz operational frequency. Another way to lower the operation voltage and boost the sensitivity is to use high-K dielectric, which has been reported before. And this simulation shows a structure of 50 nanometers gap height and 50 nanometers insulation layer thickness. And we can see that with high-K dielectric, we can achieve a larger proportion of electric field in the cavity, which gives us a higher efficiency. So now the question is, how can we incorporate this high-K dielectric in our process? We tried several implementations. Putting the high-K dielectric layer on the SOI wafer or on the glass surface will lead to a bonding failure because of the oxygen cannot diffuse through the high-K dielectric layer for efficient anodic bonding. Another way is to etch the dielectric layer on the glass post, but this requires a very high selectivity between the hafnium dioxide and the glass, which is difficult to achieve. And finally, we were able to deposit the hafnium dioxide using a low temperature ALD process following the metal deposition, and we lift the two layers together. The AFME image shows the hafnium dioxide is defined in the cavity. Our current device has a relatively large cell size and a thicker sandwich structure plate, and the insulation layer is on the plate side. And with our current process and verified steps, we propose we can achieve the ideal device structure, which has a single crystal thin plate, smaller cell size, and has hafnium dioxide insulation layer in the cavity. We can also use 2-micron post width and use the rectangular cell design and 10 structures to improve the fill factor for a broadband. To summarize, in this presentation, we have demonstrated a high-frequency broadband 1D CMUT array fabricated using only 3-step photolithography. And our device shows 29 MHz center frequency and 100% fractional bandwidth. And the design guidelines for high-frequency broadband CMUT arrays are discussed. A thin plate, smaller lateral dimensions, thin gap, high fill factor, and using of a high-K dielectric is required for high-frequency broadband CMUT operation. And we have demonstrated process modules to achieve broadband at higher frequency. And finally, with our reported TGV process yesterday, we propose we can fabricate 2D high-frequency broadband CMUT by using the through-glass vias. This concludes my presentation. Thank you very much, and I'll stop here and take any questions.